Okay, good morning. Welcome back. Happy dreary Monday. Today is class number 6. Today we're going to introduce derivative formulas, which for many of you is going to feel like a breath of fresh air compared to the drudgery of finding derivatives with the limit definition. I'll remind you of what that means. Coming up, we've got polynomial optimization problems. I think I mentioned a few classes back that the order of our course has been completely reshuffled from what the authors of the book intended, because we have been sprinting to that class right there. So that's been the goal of this sort of crazy reshuffle we've been doing. We're actually going to get a jump start on this material at the end of today's class. Coming up, quiz number 1. It is a take-home quiz. All of our quizzes are take-home quizzes. I'm going to hand that to you on Friday. You are going to work on it over the weekend and hand it right back to me Monday morning at 8:40, okay? I'll give you more details about what's involved on Friday. The projects are due September 28 and September 30, so definitely coming. Hopefully we've been making good progress on each of these. This coming Friday is our project check-in day. You'll want to come into that day. Hopefully as far into the projects as possible, ideally right on track with the suggested timeline. Okay, any questions on the calendar? Okay, so I mentioned we're starting on page 34. This is actually several pages earlier than we really are for today, but I just want to remind us of something that hopefully we had a chance to do during class, during the activity last time. This problem at the top said use the limit definition of the derivative to find f prime of x, remember that means derivative, for this function, f of x equals the square root of x. And so I'm just going to zip through this calculation. I don't know that everybody had a chance to do it, but I just want to show you the pain that is this calculation so that we will appreciate the shortcut formulas that we're going to introduce today. So the limit definition of the derivative always starts the same. It is always this thing, including that limit stuff in the front. And then we replace, instead of f of x, what is it in this case? Square root of x, so that is right there. And then f of x plus h, some people still have trouble plugging the x plus h in. We got to get good at that. It means that you replace all of the x's with x plus h, and so that is this piece right here. Okay, and then we've got some algebra work to do. In this case, the trick is to multiply top and bottom by the conjugate of wherever the radicals are. It's up here. So I have multiplied by this stuff in purple, square root of x plus h, and then I change that to a plus square root of x. So that is up there, and then I just have to multiply the bottom because I multiplied the top. And then we FOIL or distribute, and we multiply here. What do we get? X plus h, that is this guy. And then we multiply the outers, and we get square root of x times square root of x plus h, which I didn't write down, because when you do the inners, you get negative square root of x, square root of x plus h, and they just magically cancel. That's the goal with multiplying by the conjugate. And then finally, the last, what do you get? X with a subtract in the front, right? So that is that minus x. And then miraculously, good things happen on the top. The x and the minus x cancel, and then what can you do? And then you can cancel the h with the h that's on the bottom. So h goes away. We are still left with a 1 as a placeholder on the top. And so that's what we've got here, 1 over square root of x plus h plus square root of x. And then finally, we get to plug in h equals what number? 0, because we've been waiting to do this limit as h approaches 0 the whole time, and now we can finally do it. So literally, we are just replacing the h with a 0. It is here in orange. And then this is just the square root of x plus another square root of x gives me 2 square root of x on the bottom. Nick?
Now, form of this has h to the bottom, so it seems like you want to do that all the time. Like, oh, I can do h to the top.
Yeah, the conjugate comes into play when we have a radical. If the original function had been a polynomial, it would be a different technique. If the original function had been a fraction, it would have been a different technique. But for radicals, this is the standard technique. Okay, and so the point is that if you start with the square root of x and you say, what's the derivative as a function? The answer is 1 over 2 square root of x. And so today we are going to introduce formulas that will get us very quickly and efficiently from the original square root of x to our final answer where the derivative is 1 over 2 square root of x. That's the goal, right? Avoiding this stuff in the middle. Okay, we're jumping ahead to page 42. At the top, our daily summary. In this class, we see our first derivative formulas. We're actually going to see a number of different derivative formulas over the next few weeks. Here are the first few. First, some notation. We're going to see this notation formally in a few classes, but we're going to just introduce it today and use it today. If you see d over dx and then some brackets, it's crazy looking notation. It simply means the derivative of what's in the brackets. So d over dx at the moment really doesn't have any context for us. It will soon, but it means the derivative of what's in the brackets. Okay, here's our first shortcut rule. If c is a constant, then the derivative of c is 0. Most of the shortcut rules we're going to develop today are not going to be intuitive. They're not going to be obvious why they're true. You're just going to trust me on it, and if you want to see proofs, you can read the book or ask me outside of class. But this one, actually, I'm hoping we understand. Show me with your arm what the graph of y equals any constant looks like. With your arm, right? Just a horizontal line. Y equals a constant. And so what's the derivative? What's the slope of this horizontal line? It's just 0. So the derivative of any constant is 0. We've got it written here in words as well as the symbols up there. So what is the derivative of -7? 0. Fill it in. Derivative of any constant is 0. Trust me, the derivative rules are going to get harder. Next one, the power rule. If n is any real number, then the derivative of x to the n, that is x to a power, is n times x to the n minus 1. So in plain English, written in bold here, what you do is bring the power down. So this n came right down in the front. You copy the x, that's that guy right there, and you subtract 1 from the power. It used to be n, it becomes n minus 1. This should not at all be intuitive. Not at all. But there's a proof for it. You can see it in the book, or you can ask me. Let's see if we can use it. The derivative of x to the 6th. First thing, I'm just working off of the English definition here. You bring the power down. What comes down? 6. What do we copy? X. And then for some reason, we subtract 1 from the power, and we get 5. That is the derivative, 6x to the 5th. I just want to point out that the way to find the derivative of x to the 6th before we have this fancy shortcut is to do a long expression, long calculation like the one that we just did for the square root of x. Actually, even longer than the one that we just did for the square root of x. But now we've got this wonderful shortcut, so we use it. Derivative of x to the -4, what comes down? -4. What do we copy? X, and then -3 power. All right, so I got some people very angry with me, which is great because I made a mistake. But if you bought into that -3, then you were right there with me making this very easy mistake to make. You subtract 1 from the power. I did not do that. What is it? -5. Be really careful. As a species, we are not as good with negative numbers as we are with positive numbers. So just be careful. Okay, last one here. Derivative of the cube root of x to the 5th. At the moment, this is not in a form that we can use our fancy new power rule on. The only thing we can use our power rule on is x to a number. So the first task is to do some pre-calculus on this guy and make it look like x to a number. So go ahead and copy the funny new notation. D over dx just means derivative of. I'm going to put a big blank up there. And so 5th root, no, cube root of x to the 5th. What's the power? 5 over 3. Remember that? It's like an algebra kind of thing there. So 5 over 3 goes right up there. And once we've got it in x to a number form, we can use our power rule. So what comes down? 5/3. What gets copied? X, and then we subtract 1 carefully. What do we get? 2/3, right? No calculators, please. 2/3. Questions on that one? And I just want to highlight, we are always going to be using good notation here. When we rewrote this cube root of x to the 5th, we didn't do the derivative yet, which is why we were compelled to still write it there. If you don't put this, then you have told me that the left-hand side is equal to the right-hand side, and that is just not true. Right, so just make sure you're good with your notation here. Okay, number 5. If c is a constant, then the derivative of c times f of x, that is a constant times some generic function, is equal to c times the derivative of that function. C times the derivative of f of x. And then we've got a special case over here, which we'll look at. But let's just, we'll read our bold thing first. This translates to constant multiples come outside of the derivative and get multiplied after you take the derivative. It's quite wordy, but it's actually fairly easy to implement with just a tiny bit of practice. Negative 2x to the 5th. In my mind, that is negative 2 times a function, right? And so our little shortcut here says that negative 2 stays. It was multiplied by x to the 5th. It's going to get multiplied by the derivative. And the derivative of x to the 5th, well, that's our fancy new power rule. So what comes down? 5, copy the x, and then it becomes a 4. Right? And so that negative 2, all it does is multiply at the end. So it's like ignore it, and then multiply it at the end. And so in this case, we'll smush the negative 2 and the 5 together, negative 10 x to the 4th. And there isn't any point where I'm going to require you to write the negative 2 times 5. You don't need to write it. But in the beginning, until you're comfortable with this idea, I recommend just going slowly and writing it. But very soon, I suspect that we'll start to see, oh, we just bring this guy and multiply it by whatever's in the front, and that's fine. Okay, special case, going back up here, says that the derivative of a constant times x is that constant. And so that's what it's written out in words there. So the derivative of negative 24x, negative 24. You don't actually need to memorize this guy as a special case. You can do our power rule. I wouldn't, don't write this. I mean, you can if you want, but I wouldn't. I'm going to copy my negative 24. It's going to multiply by the derivative of the function, the derivative of x. Now x, hey, that's a power rule kind of thing, right? X is just x to the 1st. So what comes down? 1. Copy the x, subtract 1, and we get 0. But x to the 0 is 1, and so I've got a lot of things multiplied by 1 here, and what's the final answer? Negative 24. And so it's a shortcut. You don't need this extra shortcut, but it comes up often enough that I think it's worth just memorizing. Derivative of a constant times x is just the constant. Derivative of negative 24 times x is just negative 24. And this is one of the few that I actually do want to be intuitive to you. With your arm, show me the graph of y equals negative 24x. Y equals negative 24x. Okay, so this is just a line. Slope is negative 24, so it is going downhill very steeply, right? Maybe, right? Downhill, let me stretch before you do this one. Yeah, and what's the derivative? What's the slope of that line? Negative 24, of course, it's just the slope. Yeah, Levi. Good, okay. All right, number 7. If c is a constant, then the derivative of c over x is negative c over x squared. In English, the derivative of a constant over x is the negative of the constant over x squared. It's a special case. You actually don't need to, memorize it. I'm going to write some stuff. You can write it if you want, or you can ignore it. C over x is really c times x to what power? Negative 1, right? That's not calculus. That's just bringing the x upstairs. And hey, that's a power rule. I can do that. The constant multiple stays and waits for you to take the derivative of the function. X to the negative 1, that's a power rule. What comes down? Negative 1, copy the x, and then subtract 1. Yeah, and so that becomes negative 2, right? And if we just rewrite that in a slightly friendlier form, let's see, I see a negative sign, so that's negative. I see a c, so that's just hanging out there. And the next to the negative 2 goes downstairs and becomes x to the 2, right? So that's what it is. So it's just the power rule. It's just a special case of the power rule. But that constant over x comes up often enough that I find it worth memorizing just as its own rule. So it's a time saver. You don't need it, but I think it's worth it. So let's use our time saver in number 8, which says find the derivative of 3 over x. So 3 over x. Remember, it's always negative the constant over x squared. So what do we get? Negative 3 over x squared. That's it. Okay, what changed in here compared to the symbol we've been using the whole time? It's now a T downstairs. So that letter after the D downstairs can be anything. It's just representing the variable. So this is us starting to get a little more comfortable with things that aren't just x. So the derivative of this guy is, what do we do here? Okay, so again, it's just a constant over x, constant over variable. So what's the derivative? 5 over t squared, right? Because it's really negative the constant. So negative 5 makes us a positive 5. Nick?
The d over dx of c driven y over
That's it. Yeah. The thing that we're putting in the brackets is the y. Yeah. And we'll talk about that notation in another class soon. Okay, next page. Some indifference rules. These ones are kind of a mess to look at, but they're really easy to implement. I'll try to read the first one in symbols. It says that the derivative of f of x plus g of x. We've got two separate functions just added together. Actually, it turns out that you are able to take them completely separately, take the derivatives completely separately, and just add their derivatives up, and then that's the answer. And so that's what it says here. It says you can just take the derivative of the first function, f of x, and completely independent, take the derivative of the second function, g of x, and then just add them up at the end. And it works just as nicely for subtraction. So in English, in bold, the derivative of a sum or difference is the sum or difference of the derivatives. Let's give it a shot. Number 10. It says let's find the derivative of f of x equals negative 5x to the 4 plus 7x squared minus 3x plus 2 cubed. Then we'll find the equation of the tangent line of f at x equals negative 1. Give it a shot. Okay, we are finding the derivative, so we're going to use good notation from the beginning. F prime of x equals. Okay, first thing I see is a negative 5. Here are the two choices for constants when you take the derivative. They either get copied or they become 0. Because remember, the derivative of a constant by itself is 0. But the derivative of a constant times gets copied. So what are we doing with that negative 5? Copying it, because it is a constant times some function with x's in it. And now we're looking at the x to the 4th. That's our old friend, the power rule. 4x cubed is good, right? 4 comes down. Copy the x, subtract 1 makes 3. I'm going to leave just a little tiny space right here, and I'm going to look at my 7x squared. 7, does it get copied or does it become 0? Copied, because there's x's next to it. 7 times. Now we're looking at x squared. Let's hear from someone we haven't heard from yet today. If you haven't said anything, what's the derivative of x squared? Just say it out loud. 2x. Right? 2 comes down, copy the x. You don't need to write it, but what's the power when you subtract 1? It's 1, which is why you don't need to write it. Okay, I've left a little mysterious space there. I'm going to leave another one here. There's a 3x there. That's one of our special cases. The derivative of a constant times x is just the constant. So what's the derivative of 3x? I'm leaving the space for the minus. What's the derivative of 3x? It's just 3. Okay. And then I'll leave one last little space, and I'll look at my 2 cubed. That looks like a power rule. 3 comes down, copy the 2, subtract 1. Yes? Yeah, 2 cubed is a constant. What's the derivative of any constant? It is 0. Don't be distracted by the fact that 2 cubed it looks like x cubed. It behaves completely differently. There's no x. So the derivative of any constant, regardless of what form it is in, is 0. It's really easy to miss that. Start applying the power rule everywhere. Okay, I left 3 mysterious spaces there. Let's fill them in. Our rule up above says that when you have functions that are added and subtracted, you can just do derivatives completely separately and then add and subtract at the end. we treated this negative 5x to the 4 completely independent from that 7x squared. And that rule at the top says you're allowed to do that. And what do we do at the end after we've done our separate derivatives? We add them. So we just add them. Plus there. And then the next sign was a subtract 3x, so we just put a minus there. And the last sign was a plus 2 cubed, so plus 0. Okay? That's how we apply that top rule. Add and subtract, you get to just completely separate, add and subtract your answers. Okay, we clean this up a little bit. You get negative 20x cubed plus 14x minus 3. There is our derivative function. Any questions on that calculation? And if you do have some previous calculus experience, this is probably what you think of when you think of calculus, is just taking these derivative rules, and you've done many polynomials like this. My expectation is that none of you has seen this before, so just recognize there's very different experiences sitting at our tables here, and so some people are just going to zip through this because they've had all the practice with this already. If this is your first time, take your time. We'll get there. There's no rush. Okay, so follow-up question. The equation of the tangent line of f at x equals negative 1. All right, let's give it a shot. So in order to find the equation of any line, we need two pieces of information. We need a slope and we need a point. Sometimes that point is the y-intercept, but slope and point are the two things we need. All right, let's find the point. We need a point that is on the equation, that is on the graph of that tangent line. 0, negative 3, wait, what? Yeah, so if you plug 0 into the derivative, you get negative 3, but I don't think that's what we're after here. We need a point that's on the line. Let's just draw the line real quick. At x equals negative 1, go ahead and put a dot on the graph at x equals negative 1. So x equals negative 1 is pretty close to that top point, but I think it's a little left of that top point. And so just a very quick sketch. You don't even need a straight edge, but draw that tangent line right now. So I see a line that is going slightly uphill, not too steep. Everybody with me on that? We're trying to find the equation of that line. We need a point that is on that line. There's only one point that we have any chance of finding on that line. Where is it? It's at negative 1, right? That's the only one we know. We don't know anything else. Everything else is just floating in space. So we need to know what's going on at negative 1. Well, okay, so we know that x is negative 1. What we don't know is the y value. How do we find the y value at that point? We plug it into what? Into the original formula. This has nothing to do with calculus. This is just finding a point on the curve. So then we need to find f of negative 1. Not f prime, but f of negative 1. Okay, so we're plugging negative 1 into that original formula. I'm just going to sort of skip some of the steps here, but negative 5 times negative 1 to the 4. I think that's still negative 5, right? And then plus 7 times negative 1 squared. That is still plus 7. And then minus 3 times negative 1 becomes, so this is now a negative 1. Minus 3 or plus 3? Plus 3, right? And then finally plus 2 cubed. 2 cubed is 8. So we crunch the numbers, no calculator here. I think it's 13, is that right? Okay. Yeah, we're just plugging negative 1 into the original. So f of negative 1 is what we've written. So that means that the point we have is negative 1 comma 13. Great. Like I said, we're finding the equation of a line. This is something you've done for many years now. Still need two pieces of information, the point, which we just found, and the slope, which we need to find. But we know that the derivative is, remember this is the part we chanted, the derivative is the slope of the tangent line. So really what we need is the derivative. Hey, great, we found the derivative. It's this thing here in blue. What do we do with that thing in blue? plug -1 in. It's another common misunderstanding for folks here in the beginning, is that they think, oh, the slope is, like this thing right here. This whole thing is the slope, and I'm just going to use the mx plus b, and I'm going to put this whole thing for m. That's not right. This is the slope for any x. We don't want the slope for any x. We want the slope for the particular x we're interested in, which is -1. So let's plug in to the derivative, -1. Okay, so we're just going right here. When we plug -1 for x, does this piece is this piece here positive or -1? That's -1, which means when I multiply by the -20, I get 20. Okay, and then we're doing -1 for this x. What do we get? -14, and then copy the -3. -14 minus 3. Is that 3? Okay. Seems reasonable. It's positive, right? Uphill, not terribly big. Okay. And now really going old school with your finding equations of lines from previous classes. There's two typical options here. There's the y minus y1 version. I'm guessing that most of you prefer the y equals mx plus b version. I think this is the one that we're going to use mostly in this class because that's my expectation for what you want to do. But really, it doesn't matter to me. Just be good at one of these. Using this guy, y equals, we found the slope is 3. So we go y equals 3x plus some y-intercept, which we don't know yet. And then we need to find that y-intercept by doing what? Not 0. -113, that's the point that we know, right? So 13 equals 3 times -1 plus some b. Is that green too light? Can you guys see this in the back? It's not great. All right, I'll make it darker next time. Or 13 equals 3 times -1 plus b. Okay, so then we just do some work. 16. All right, okay. So b is 16, which means the equation of our tangent line is y equals, where'd it go? 3x plus 16. It's funny, I find myself pressing harder into the smartboard, trying to make it darker for you guys in the back. Doesn't do much. Okay, that's it. That's the equation of a tangent line. Finding equations of tangent lines is a fundamental process in Calculus 1. You're going to be doing it a bunch.
We go through like 3 processes. You plug in the original equation, slope, and you plug that into the slope function.
So you said slope function, you mean which equation?
Derivative.
You plug into the y equals mx plus b.
Right,
yeah, right, exactly. That's exactly the process. We did a little bit of work in our heads. This was -3, and then solving for the b, you have to add the 3. So 16 for b. Okay, so what is going to happen right now is you are going to work on this group activity. Turns out that next class is a long class, and so we're actually going to steal the last 20 minutes of today's class to jumpstart the next class. I'm not assigning 2 homework assignments. I just want to get a jump start on the material for next class. So you're going to have about 21 minutes from right now to do as much of this activity as you can. I want to shorten this activity just a tiny bit. Part C says check your answer by graphing the function on the calculator. I'm going to say just skip that part in the beginning, and if you finish all of these, then go back and check it. Okay, so you're going to be finding a formula for the derivative using our new shortcuts, and then you're going to be finding the equation of a tangent line. I will walk around.